Welcome to this lecture. This is a lecture in module 2. Its title is Effective Current and Logical Effort for Near Threshold Voltage Combinational Gates. So, we have already done in the previous lectures, we have derived an effective current model for near threshold voltage inverter and for a near threshold voltage NAND gate with lower transistor switching. So, today in this lecture we will do an effective current model for near threshold voltage NAND gate with its upper transistor switching, and then we will discuss how logical effort is related to these effective currents, and then we will discuss the how one can consider logical variability in logical effort in near threshold voltage regime at an early stage of design. So, in the previous lecture we had discussed the case where lower transistor is switching and we had obtained the values of IH and IL, which gave. So, we divided the entire discharge output discharge into different regions, and in one of the regions the current is increasing linearly. So, there we identified the endpoints and therefore, we get the average discharging current in this region, and then we had obtained the value of this constant, almost constant current, and using these two we had computed the values of effective switching current from this point where the output begins to discharge to 50% of the time when output reaches 50% of its supply voltage value. So, in this lecture we will discuss the upper transistor switching. So, now A is at VDD and upper transistor switches from 0 to VDD, and VA can be given by VDDT by TR, where TR is the transition time. So, what do we observe here? The input rises. Prior work before this paper, the prior work was referring that the input, when it reaches 50%, the output would start discharging, which is not true for near threshold voltage regime. Here, even for the balanced stage effort case where the input and output transition times are equal, even in that case it is not at the 50% of input value that the output discharge begins, but at a value called V in C, which we have derived and which is nearly 75% of the input voltage final value, 75% of VDD near at. So, that is where the output begins to discharge nearly. So, here what we observe is that once node X is initially at 0 volts, because this is at VDD and this is at 0, B is at 0 initially. Once the input begins to switch to a higher value, there is a current that would start flowing. So, this case is almost like that of an inverter. Now, the node X is at 0 volts, and like for the inverter, the current starts assuming an important value and the output begins to discharge only when the input reaches around 75% or V in C, 75% of VDD or V in C to be more correct. So, and this V in C would be the same as that of the inverter's V in C when the output begins to discharge. V in C is the input voltage value when output begins to discharge, and it would be similar to that of the inverter, because node X is at 0 volts. So, nearly at 0 volts, and therefore, it is M2 behaves just like the pull down transistor of an inverter. But once M2 begins to discharge the output, there is a current through M2, discharging current, and that must also flow through M1. So, for it to flow through M1, we would find that the node X must assume a voltage, a non-zero voltage value, and therefore, node X slightly rises after the output begins to discharge. Node X slightly rises, and then during the entire discharge it rises, and during the entire discharge, say till the 50% or till this point, it remains almost at a constant value. So, the entire discharge process is almost at a constant value of node X. That is because if the voltage at node x changes, suppose it increases, then VGS of M2 would reduce. VGS of M2, if it reduces, then the current through M2 must reduce. Okay. But the current through M2 is almost constant after this point, okay, when the output reaches 80% value, like in an inverter. The current through M2 is almost constant. So, since the current through M2 is almost constant here, the value of VGS of this cannot significantly change. VGS of M2 cannot significantly change, and therefore, node X must remain at its value. Or if this changes, then the current through M2 reduces. If it increases, suppose node value of node X, voltage value of node X increases, then the current through M2 reduces, and current through M1 would increase because its VDS is increasing, M1's VDS is increasing. So, it cannot happen that way. So, this is inconsistent. So, it would never happen that way. And why is the current through M2 almost a constant after the input reaches 80% value? As we see, the input now rises very slowly because of the back coupling from CM, and the output is falling rapidly. So, as in the case of inverter, you have a constant current here. So, what is the value of IL here? IL is this value when the input begins to discharge. ID of an N MOSFET for Vg equal to V in C. Now, this is the V in C of an inverter, which is again valid for this 2 input NAND gate with upper transistor switching. Vd equal to VDD, which is this value, Vs equal to 0, Vb equal to 0, body voltage. Okay. This is same as the V in C of an inverter. So, what is the value of Ix, IH? So, now as we had discussed, the value of current voltage Vx would remain almost constant from 80% value of V out to 50% value of V out, and in fact, till the time V out is discharging, it would remain almost constant. The reason we have just discussed. So, for IH, we need to take, this is the value of IH, isn't? So, for IH, we would take it as IDS Vg equal to 0.95 VDD. This is 0.95 VDD. Vd is equal to 0.5 VDD, that is the point where we are taking IH. It is constant, almost constant from 80% VDD to 50% VDD. Vs is equal to 0.075 VDD, and now this 0.075 VDD is valid for all the fan out loads because of 1-to-1 correspondence between input and output voltage values. It could be slightly different for different PDKs. So, we need to extract it out once for one of the FOs, and then it is almost the same for all the FOs, and body voltage we are taking to be 0 volts. So, this is how we have obtained IL and IH. Now, let us look at effective switching current for NTV gates. For lower transistor switching, this VNC, so this VNC is different from that of the inverter, and for upper transistor switching, this is same as that of the inverter. Okay. Now, we have these two values. What is the value of effective current? Now, as in the inverter's case, we have divided the regions in the same way. So, from 50% input value to V in C, from V in C to 80% of the output discharge. V in C is when the output begins to discharge. V in C to 80% of the output discharge, 80% of output discharge to 50% of output discharge, there is a constant current. So, there is a linear current, increase in current from V in C when the input is V in C and output is, and to the time when the output voltage is 80% of VDD. So, there is a linear increase in the discharging current. This is same for inverter, for upper transistor switching in a NAND gate, for lower transistor switching in a NAND gate. Only thing is that the value of V in C keeps changing for all the 3 cases. And from 80% of output voltage value to 50% of output voltage value, there is almost a constant current, and this happens for the inverter, for upper transistor switching in a NAND gate, for a lower transistor switching in a NAND gate. Therefore, the effective current model remains the same. So, the effective current model for NAND gate would also be IH into IL plus IH divided by 1.9 IH plus 1.1 IL. The only thing is that IH, IL would be different for inverter, for upper transistor switching and for lower transistor switching in a NAND gate. For all the 3 cases, IL and IH would be different. Otherwise, I effective's relationship with IL and IH would remain the same. So, how do we compute logical effort using this effective current model? How do we define effective current? We define it as delay of a gate is equal to half CL VDD. Okay. So, this is for 50% discharge at the output divided by I effective. And how do we define logical effort? So, in this we can also refine this as half Cp VDD if we want to look at the total output capacitance as a combination of logical effort of load capacitance and a parasitic capacitance. We can also write it as this, isn't it? So, and we know that Cp and I effective both are, the parasitic capacitance and I effective are both proportional to transistor width ideally. So, therefore, this would come out as a parasitic delay. So, how do we write logical effort? How do we look at logical effort? So, there delay is equal to G into H, which is CL by C in plus P parasitic delay. Okay. So, P parasitic delay is the same as this is P, okay, because this is not changing with width. What about the other term? So, how do we obtain the value of G? For an inverter, G is equal to 1 for a template inverter. So, let us write template or reference inverter, G is 1. So, we would say that delta by C in, delta is the intrinsic delay, delta by C in should be equal to VDD by 2 I effective, like that. Okay. Now, for any other gate, so this is for the template inverter, for say NAND gate, G is not 1. So, there we would have G into delta by C in NAND that would be equal to VDD by 2 I effective NAND, is not? That is the way we would write, because there G is not 0. So, what is the value of G of the NAND gate? This is the same as this G. So, what is its value? So, it would come out to be I effective inverter by I effective NAND into C in NAND by C in inverter. So, what we obtain is that we can relate effective currents and logical effort values. We can also relate effective current and parasitic delay values. So, how do we obtain the logical effort of a? So, we have discussed how we obtain the logical effort of a given gate from its effective current values. For near threshold voltage regime, we will see in the coming lecture that the template inverter could be different from an inverter having some other layout. So, there the logic, we can also define logical effort for inverters having a different layout compared to the template inverter. We will discuss that in the next lecture. Presently, let us try to understand how we can include variations in logical effort or effective current models. Since we have defined the logical effort and effective current models in terms of IH and IL, where we have this V in C, where the output begins to discharge, and that also we have derived. So, suppose a change in VDD, variation in VDD is to be accounted. We can account the variation in VDD through the variation in IL, IH, VNC, etc. So, all these 3 parameters, and understand the variation in compute the variation in logical effort directly. Likewise, suppose the threshold voltage changes, then the current, how it current relationship with threshold voltage we know, and therefore, a change in threshold voltage, how much is it going to change the value of logical effort can easily be computed. Likewise, suppose there is a variation in the value of mobility. With mobility, how IH, IL change we can compute, and thereby we can compute the change in logical effort. So, a change in parameters associated with variability in near threshold voltage regime, which are VDD, threshold voltage, mobility, temperature. Temperature changes threshold voltage and mobility, and through the change in threshold voltage and mobility, we can estimate the change in IH and IL, and thereby the change in logical effort. So, the change in logical effort can be computed from change in threshold voltage, mobility and VDD, and therefore also temperature. So, PVT variations can, what is the impact of these variations on logical effort can directly be computed using this approach. So, in this lecture we discussed the upper transistor switching in a NAND gate and the effective current model for that, and then we discussed how logical effort is related to the effective current models, and how using this approach we can include variations in temperature, threshold voltage, mobility and supply voltage in calculations of logical effort. So, once we can obtain the logical effort using simulations and how it varies with these parameters, one can directly compute thereafter. Thank you.